All right. So the next one is called conversion equations. So I'm going to go start a new file. And for conversion equations, we're talking about temperature. It's not the only time you would use it ever, but it's the only time I use it in this class with temperature conversions. And why do we need a special equation? Because the zeros are defined differently between centigrade and Fahrenheit. And because their zeros start at two different points, we can't just multiply by 1. It makes no sense. We need to do something else. And so there's a simple equation, and that equation is in the handout. And a little over halfway down, I think it is. Where did they go? There they are. Centigrade equals degrees Fahrenheit minus 32 in parentheses, so you do that first, divided by 1.8. Or degrees Fahrenheit equals centigrade times 1.8 in parentheses, so do that first, and then you add 32. So they're both the same exact equation. They're just rearranged. It's introductory algebra to rearrange those equations. But you could start with one and come up with the other just by doing simple solve the one on the left for degrees F and you get the one on the right. Solve the one on the right for centigrade for C and you get the one on the left. Now maybe you've learned the temperature conversion using 5/9 and 9/5, which is fine. What is 5 divided by 9 or 9 divided by 5? 9 divided by 5 happens to be, oh, look at that. 5/9 is 1.8. What did I have? 1.8. It was just cleaner to write it that way. I learned it with 5/9 and 9/5, but it doesn't matter. And if you forget the equation and you're trying to remember, you know, you kind of got it in your head and you don't have access, do something really simple that you know, like 0 centigrade equals 32 degrees Fahrenheit, the boiling point of water. So let's do that one. 0 centigrade equals what? You know it's going to be 32 Fahrenheit. You should memorize that one. But I'm going to do an equation just to prove that it's 32. So what is my unknown? My unknown in this case is Fahrenheit. So because Fahrenheit is the unknown, I want to pick the equation on the right where Fahrenheit's already by itself. So centigrade times 1.8. And in the table, the asterisk is actually the same as the multiplying sign. When I did this originally, I didn't have a times symbol in my font set, and so I used the asterisk, which is fine. It's the same symbol that's on your calculator, possibly. It certainly is on mine on the computer keyboard. And I add 32. Now this one's really easy. This is 0 times 1.8. What's 0 times 1.8? 0. Anything times 0 is 0. So 0 plus 32, my answer is 32. So that tells me I've got the right equation. Let's try something a little more challenging. Let's try 37 centigrade. So that's going to be 37 times 1.8 plus 32. And 37, oops, $66.6. Plus 32. 98.6 normal human body temperature in the American Fahrenheit system of temperature measurement, 98.6. And so all you really have to do is remember, if there's a temperature equation, to look at the table that I give you and pick the one where what your unknown is already alone on the left. If I'm looking for Fahrenheit, pick the one on the right. If I'm looking for centigrade as my unknown, pick the equation on the left. These are pretty easy with a little bit of practice. You just have to remember to pay attention. An example of where you might have to pay attention a little more is, let's say I do 17 degrees Fahrenheit. What is that in centigrade? Well, I'm looking for centigrade, so I need degrees Fahrenheit minus 32. Degrees Fahrenheit minus 32 divided by 1.8. So there's my equation. What is it? 17 minus 32 is minus 15. Don't forget the minus in that number. I subtracted, it's minus 15, negative 15. So negative 15 divided by 1.8, and 17 degrees Fahrenheit divided by 1.8 is minus 8.333333333 minus 8.3, and you put this little line over it to say it's continuing indefinitely. You don't have to do that. If you gave me minus 8.3 on a test, I'd mark it right. But that little line is called a vinculum, and it comes in handy for repeating numbers. And the only reason I know it's called a vinculum is because I was trying to write a lab book for the soil science class, and I needed a vinculum, and I had no idea what the heck to call it. And I had to do some hunting. How the hell do you do a vinculum in Microsoft Word? Or how do you do the line over a number, over a 3 in Microsoft Word? And eventually I found that it's called a vinculum, and I found out how to do it. But yeah, the answer, 17 degrees Fahrenheit is less than 32 degrees Fahrenheit, which means it's less than freezing, right? And if it's less than freezing, you're going to end up with a negative number, negative 8.3 centigrade, or degrees Celsius. All right. Which leads me to the last type of problem. And we call this, or I call this, my order of magnitude problems. And you can do these problems using the order of magnitude table here, the table 2 prefixes, and these powers of 10. Or you can do them by just using a conversion factor. You can do it using a conversion factor. The problem is the conversion factors are so cumbersome with so many zeros that it's prone to error. So the way I'm going to show you is what I think is the easiest way to do them and the least error prone. The problem is, I think, a lot of students tell me, oh, it looks so easy, I thought I could do it on a test. And they didn't practice. And they forget the process because it's not something you've done before. Practice. And then practice some more. And then practice some more to make sure you've got it down, and then just double check. Pull up those sample problems on the Canvas modules and practice some more just before the test. Make sure you got it down. These are not hard problems. Let's say you have something like this, 22 million nanometers equals how many megameters? No, let me do kilo. Kilometers. 22 million nanometers equals how many kilometers? So you can recognize these problems because they have very big or very small numbers on my tests. You can also recognize them because they're metric on both sides. I've got nanometers and kilometers or kilometers. Metric on both sides. And the same unit, meters. It's only the prefixes that's changed. That's an obvious order of magnitude problem. Now, where do I run into this in agriculture? Why the hell am I telling you this? I ran into it all the time. Now, there's a lot of math that I'm going to say is in a black box that we're not going to get into. You're welcome. There's a whole bunch of difficult math, and I'm only doing the last simple step. Let's say I am doing an experiment in the greenhouse, and I'm using a little device called a micropipetter, and I'm putting 2 microliters of some sort of chemical on my plants in a little 2-inch pot to see how they behave. And it looks interesting. It's like, wow, you know, my little 2-inch pot experiment in the greenhouse looks promising. Let's try it in the field. So if I'm using 2 microliters in the field and my first set of calculations, I determined that I need 87 million microliters per acre. What the hell does that mean? How many is 87 million microliters that I'm going to spray on my actual plants in the field? I need to convert that to something more manageable, like liters, right? Well, here I've got kilometers. It's the same process. So let's figure out how to do it. And we use that table that I showed you a moment ago and look up what is the power of 10 for nano and kilo, and also which one is bigger and smaller. So let's start with that. Which one of these is big and which one is small? Is nanometers small versus kilometers? Which one is the big one? Kilometers is big, right? Nanometers is really small. So am I going to need a lot of nanometers to equal kilometers? Or am I going to need a lot of kilometers to equal nanometers? No. I need a lot of nanometers to equal kilometers. I need less kilometers to equal nanometers, right? I've got to bring the kilometers down. I need less of them. How do I make a number less? I move the decimal to the left. So that's step 1. Do I need more or less of these? I need less of them to be equal. I need less kilometers to be equal to nanometers. I'm going to move my decimals to the left. That's step 1. Step 2, I need nano and kilo. What is nano? Nano is 10 to the minus 9, and kilo is 10 to the plus 3. Nano is 10 to the minus 9, and kilo is 10 to the plus 3. What is the distance between -9 and +3? I'm asking for a distance. It's always a positive number. To go from -9 to 0 is 9 hops, and then to 0 to 3 is another 3 hops. So it's distance, a total distance of 12, right? From -9 to +3 is a distance of 12. And I'm going to move my decimal 12 places to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I probably shouldn't have started with that one. Probably wouldn't give you one like that. And I fill in the zeros between each of these humps, and my answer is 0.000022 kilometers. 0, and there's 4 zeros. Now, had I warmed up a little bit, I probably wouldn't have used nanometers. I would have used micrometers. Or maybe I would have used millimeters. Let's try it with millimeters. What would it be with millimeters? The same thing, 22 million millimeters to kilometers. How many kilometers is 22 millimeters? All right. Well, kilo is still 10 to the 3. Millimeters is 10 to the minus 3. What is the distance between 3 and negative 3? It's a distance of 6. From negative 3 to 0 is 3 hops. From 0 to 3, positive 3, is 3 more hops, a total of 6. The distance is always positive. So now if I have my 22 million, my decimal place is currently here. And so 1, 2, 3, 4, 5, 6. My answer in this case is 22 kilometers. 22 million millimeters is 22 kilometers. All right. Or maybe I've got to do this one in a different direction. Maybe I have something like 0.0000 microliters equals how many liters? Are liters big or small? Do I need less of them or more of them? Oh, excuse me. .0009 liters, I'm sorry, equals how many microliters? I, again, so worried about trying to do this on the tablet. So there's our new problem. I've got 0.00009 liters. How many microliters is that? Well, 0.0009 liters, I'm in metric. Microliters, I'm still in the same units, or the same, the same units of metric, liters. I just have a different prefix. So do I need, which one is bigger? Do I need more or less microliters to be equal? Do I need more of them or less of them? Well, are liters big? Microliters small? Yeah. Liters are big, microliters are small. So that means I need more of the microliters to be equal, don't I? I need more. And how do I make a number bigger? How do I make a number more? I move the decimal to the right. How far to the right? Let's look at the prefixes. First, microliter. Micro is right here at 10 to the minus 6. 10 to the negative 6. And what about liters? What's the power of 10 for liters? We're looking at the prefix. What's the prefix for liters? There is none. There is no prefix in this particular problem. It is just liters, and that's where we use 10. What did I do? Damn it. 10 to the 0 power. 10 to the 0 power is what you use when there's no prefix, when it's just 1 liter. There's no prefix, 10 to the 0. So I use 10 to the 0. And I ask myself, what's the distance between the exponents? The distance between 0 and negative 6, the distance is 6. And I'm going to move my decimal to the right. 1, 2, 3, 4, 5, 6. So my answer is 90. Just fill in zeros and those extra hops. If I needed to write this down out of the way. So my L, my liter symbol was out of the way and I needed more room, fine. But you can see that there was one extra hop. My decimal place started right here and I moved it over 1, 2, 3, 4, 5, and 6. The answer is 90. And those are the order of magnitude equations. I think they're easy. I think most students, when they look at them, they think they're easy, but they get them wrong on my midterms and finals all the time. People lock up because they don't practice. It's not something you do very often. It's not something you're exposed to before, and you think it's easier than it is, and you don't practice. Practice. All right? And that, for now, is it for the metric system.